Chapter 6 of The World's Lumber Room by Selina GAYE. This LibriVox recording is in the public domain. Chapter 6. Dust Makers, Earthquakes and Volcanoes. We referred in the last chapter to the possible rise of the bed of the Atlantic at some future period above the waves, and we have now to see how this might be brought about. It is a well-known fact that sea and land have many times changed places, and that by far the greater part of the rocks composing the earth's crust must from their character have been formed under water. It has also been ascertained by careful observation that at the present time Norway and Sweden are quietly rising higher and higher out of the German Ocean, at the rate of 3 feet in a century. And on the eastern coast of South America there are large beds of shells which have been raised, some a few feet only, others as many as 300 or 400 feet above the sea, in what geologists would call quite modern times, while at Santa Cruz a rise of at least 1,400 feet has taken place since the time when the great boulders with which the plains are dotted were dropped by glaciers or icebergs. On the western coast of America the evidence as to the way in which sea and land have changed places is even more striking, and shows that the vast mountain chain variously called the Cordillera, Andes and Rocky Mountains, which apparently stretches in an unbroken line from Tierra del Fuego to the Arctic Circle, with pinnacles here and there reaching a height of 20,000 feet, has risen and sunk again certainly once, and almost certainly twice, in the course of its history. In the Uspallata range, which is separated by a narrow plain from the main mass of the Cordillera, there stands a group of snowy white columns a few feet high, which have a weird, ghostly look about them, and are evidently the trunks of trees which have been petrified and converted, some into flint and others into coarsely crystallized spar. Now, these stone fir trees have had a wonderful history. They must, of course, have grown upon dry land, but below them are several thousand feet of rock which could have been formed only under water. Therefore the land hereabouts must gradually have sunk lower and lower until it was many thousand feet below the surface of the sea. Then, when these new beds had been formed, it rose again, and when the soil had been prepared for them, a beautiful group of trees sprang up and flourished on the shore of the Atlantic, which then washed the foot of the mountains, though it is now 700 miles away. The trees grew to maturity, and then the land began to sink again. But this time it was let down to an enormous depth, much greater than before, for the firs were buried under beds of sediment as thick as those upon which they stood, and besides this, streams of lava from a submarine volcano flowed over them, one being a great mass of black basalt, 1,000 feet thick. After being thus buried, the trees were once more raised, and this time hoisted up 7,000 feet above the sea, and now, by the wear and tear of time, they have been exposed to view and stand high up in the mountains and hundreds of miles inland, like ghosts of their former selves. Similar risings and sinkings of the land have gone on, and are still going on, more or less, all over the world, so that it is quite true, as has been said, that nothing, not even the wind, is so unstable as the crust of this earth. As to the causes of this perpetual motion, scientific men are at present by no means agreed. On whatever part of the earth's surface we may be standing, we are something less than 4,000 miles from its centre. But the deepest mine in this country has not quite been carried to the depth of even half a mile, which is a mere scratch in comparison. What would any one know of a coconut if he had but scratched its shell? And yet a scratch on a coconut shell would be proportionately far deeper than the deepest cutting we have yet made in the crust of the earth. We may argue, indeed, that because the mercury in a thermometer is found to rise on an average 1 degree for each 60 feet that it is carried below the earth's surface, therefore at the depth of but a few miles the heat must be so intense as to melt any rock with which we are acquainted. And if we can also prove that the heat goes on increasing at the same rate throughout, our argument may be reasonable as far as it goes, though even then there are other matters to be considered, and we may be further justified in adding that it is the changes taking place in this molten mass which cause the earth's crust to rise and sink. But we cannot prove anything of the kind, and our knowledge of the 2,000 feet or so which we have partly explored at a few scattered spots does not give us any information as to what goes on, or as to the temperature which may prevail, at the depth of even 100 miles. All that we can say is that whatever may be the state of the interior of the globe, the heat at some spots, and these comparatively near the surface, is great enough to melt rock, and to keep water not only hot, but in many cases boiling. It is possible, therefore, that the slow movements in the earth's crust may be due to the cooling and remelting and consequent contraction and expansion of miles of rock. But whether this is really so, we are quite unable to say. Neither are we much better off when we try to find out the causes of those sudden and violent movements to which we give the name of earthquake. These are so explosive in their character that one might at times imagine them to be occasioned by the sudden conversion into steam of water which has filtered downwards until it has come in contact with heated rock. But whatever the cause, an earthquake, says Professor Huxley, is just such a disturbance of the ground as would result from a sudden shock or blow given upwards in the interior of the earth, by which tremors may be communicated in all directions through the solid rock. Footnote: the greatest depth at which the shock originates appears, according to Mr. R. Mallet, to be 40 miles, and the smallest 8. End of footnote. The more solid the rocks, the more they would feel the jar, and the better able they would be to pass it on to the rocks above, whereas in a bed of loose gravel it would be almost extinguished. If a number of ivory balls are placed in a row touching one another, a tap given to the first will be felt by all, and the last, having nothing to keep it in its place, will fly off. In a similar manner, a shock of earthquake has been known to be so violent as to send paving stones flying into the air with such force that they turned a complete somersault. It is often found that an earthquake has caused the area affected by it either to sink or rise, more generally the latter, to the extent of several feet. The memorable earthquake of 1835, which shook the western coast of South America, raised the land round the Bay of Concepcion 2 or 3 feet at one blow, and upheaved a rocky flat off the island of Santa Maria, which was left with its beds of gaping mussels hopelessly stranded 10 feet above high water mark. More havoc, too, was wrought in the island of Quiriquina by this earthquake than would have been accomplished by the ordinary wear and tear of a century. Its effects were felt far and wide, and had it occurred in Europe, the whole continent from the North Sea to the Mediterranean would, Mr. Darwin says, have felt the tremendous jar, and a large tract on the eastern coast of England would have been permanently upheaved. There is probably no place upon the face of the globe which is entirely free from the vibration of earthquake shocks, and these therefore contribute much, both directly and indirectly, to the wear and tear of the earth's crust. For besides the destruction caused in severe earthquakes by the trembling and rending of the rocks, we must not leave out of sight the often worse destruction caused by earthquake waves, when the disturbance takes place near the coast. The sea then feels the shock as well as the land. Its bed is frequently raised several feet, as by a sudden jerk, which of course powerfully affects the water above, and enormous waves are produced which rush upon the shore, carrying everything before them. In 1835, the great wave which swept along the South American coast left not a house standing in Concepcion or Talcahuano, almost washed away even the ruins of the latter place, and breaking at the head of the bay in a fearful line of white breakers, rushed up to a height of 23 feet above the highest spring tides. Its force was so great that it moved a gun and gun carriage weighing 4 tons a distance of 15 feet, but it advanced at such a deliberate pace that the people had time to run up the hills out of its way. After an earthquake which occurred in Japan in 1854, the waves continued to come and go from 10 a.m. to 2:30 p.m. Not a house was left standing in the harbour of Shimoda. Many junks were carried inland, one of them as much as 2 miles, and a few hours after the disturbance in Japan, several well-marked waves had reached the coast of California. The destruction occasioned by earthquakes is obvious enough, but even the gradual sinking and rising of the land contributes much to the wear and tear of the coast, since by this means different parts and fresh surfaces are brought within reach of the waves. The straits between islands, for instance, are worn deeper and deeper as the land gradually rises, until, when it has been lifted quite beyond their reach, the straits become mountain passes, connecting one valley with another. It has been said that, whatever the condition of the interior of the earth, we have positive evidence that at some spots not very far beneath the surface the heat is great enough to melt rock, for many a subterranean disturbance, which begins only with the quaking of the earth, ends with the pouring forth of liquid matter. A crack is made in some weak place, through which large volumes of steam and other vapours are forced up, with showers of red-hot ashes and streams of molten rock. The fall of these materials round the mouth of the hole forms a cone-shaped mound called a volcano, which usually has a funnel-shaped opening or crater. The pipe or chimney which leads down into the interior of the earth has a hard stone lining, formed by the melted rock or lava, which cements the loose ashes and cinders into a compact mass wherever it comes in contact with them. It seems probable that much of the force by which volcanic matter is driven to the surface and shot up into the air is due to the conversion into steam of water which has found its way down to the molten rock below. And whether or no this be the sole source of volcanic energy, it is certain that steam is poured forth in large quantities at the beginning of an eruption, and that with such violence that any fragments of rock which may have accumulated in the throat of the volcano are hurled into the air with much force. Masses of rock, some 9 feet in diameter, have been hurled 15 miles by the great volcano of Cotopaxi, and even larger blocks than these have at times been sent flying several miles or shot up to a height of 6,000 feet. Ashes, that is, fragments of lava or partly melted rock, which have been so splashed about as to fall in spongy-looking drops, are poured forth by volcanoes in vast quantities, and are frequently broken up into particles so fine as to be nothing more than dust, which fills the air and plunges the whole neighbourhood for miles round into darkness. Footnote: see Belt's Naturalist in Nicaragua for eruption in Coseguina. End of footnote. The most remarkable eruption which has occurred in our times is that of Krakatoa, which stands upon a fissure running across the Straits of Sunda, and until 1883 had been quite quiet for 200 years. Many earthquakes, however, had recently taken place, and it may be that a larger quantity of water than usual was consequently admitted into the depths below. The eruption began in May 1883, when the sea for 10 or 20 miles was covered with drifting pumice, through which a ship cut her way with as much noise as if it had been thin ice. The volcano continued more or less active for the next 3 months, and the worst outbreak of all occurred on the 26th and 27th of August, when an incessant rumbling was heard, accompanied by short, loud reports, as if from heavy guns. No shocks of earthquake were observed, but the blast of air produced by these explosions was so violent that walls were rent at a distance of some 500 miles. The island of Krakatoa consisted of 3 peaks, of which the most lofty was 2,700 feet high. But the whole of the northern part, with 2 craters, has disappeared in the sea, and half the remaining peak has sunk likewise, having been cut in 2 from the very summit, so that it now forms a cliff between 2,000 and 3,000 feet high. A great wave, caused no doubt by the sudden subsidence of this peak, started from Krakatoa with a height of 27 feet, dashed upon Java and Sumatra, and opposite Anyer, in the narrow throat of the straits, rose to from 40 to 100 feet, sweeping the shore of thousands of its inhabitants. The effects of this wave were felt on both coasts of America. Ashes thrown up by the volcano fell over an area almost as large as Norway and Sweden together. Dust fell to the depth of 2 inches upon a vessel 1,000 miles off, and another vessel, which was near the straits, passed masses of floating pumice 7 feet thick, which in some places were so extensive as to impede navigation. And here we must remark that, although we have hitherto considered them almost exclusively in their destructive character as dust makers, yet earthquakes and volcanoes, like many of nature's other labourers, do double work and build up as well as pull down. Indeed, it is no exaggeration to say that without them the whole of the dry land on the globe might be buried beneath the ocean. For as the rivers are perpetually engaged in wearing it down and carrying it away, they would, in time, reduce the level of the land everywhere to that of the sea, were it not for the compensating earthquake force, which, whether working suddenly or gradually, acts on the whole in the opposite direction. Volcanoes also have their share in repairing the waste of the earth's surface, and though the island of Krakatoa was reduced by the great subsidence to less than 1/3 of its original area, 20 square miles, it has since been increased more than 3 square miles by the addition of volcanic matter. The amount ejected by Krakatoa was, however, small compared with that thrown up or poured forth by many other volcanoes. Most of the islands of the Pacific are of altogether volcanic origin. Hills and islands of volcanic matter have frequently been raised to a height of several hundred feet in the course of a few hours, and lava has been poured forth in such voluminous streams as to form beds of vast extent and many hundreds of feet in thickness. Whether the molten rock which we call lava has itself been formed from something else and has previously existed in a solid state, we have no means of knowing. But there are evidently vast stores of it, for the space from beneath which volcanic matter has been ejected by volcanoes in the Cordillera alone measures 720 miles one way and 400 the other, showing, as Mr. Darwin says, the existence of a subterranean lake of lava nearly double the size of the Black Sea. A stream of lava soon cools and hardens on the surface, but the great mass within retains its heat for years. In 1759, the Mexican volcano Jorullo poured forth a perfect sea of lava, which completely filled the beds of the 2 rivers Cuitemba and San Pedro for some distance. Both streams disappeared on one side of the vast expanse of molten rock, but made their way beneath it, and reappeared on the opposite side as permanent springs, pouring forth large bodies of very hot water, which retained their heat for many years after the eruption. At the present day the water is but a few degrees warmer than the air, but for 100 years or so, large quantities of steam continued to issue from the volcano. All the Azores are islands of volcanic origin, and in one of them, San Miguel, there is an immense crater, which in former times was no doubt a lake of boiling lava, but is now a wonderfully green and fertile hollow, called, from its shape, the Cauldron of the Seven Cities, and containing 2 lakes and many villages, whose white houses, meadows, gardens, and cornfields lie at a depth of 1,500 feet below the lip of the crater. San Miguel is still shaken by earthquakes from time to time, and although there are no more eruptions, the underground fires still burn well enough to keep the water in a number of springs always boiling. These springs all empty themselves into one small stream, which retains its heat for several miles and carries down into the sea a great variety of dissolved minerals. Hot water and steam are more powerful solvents than cold water, and being usually charged with large quantities of carbonic acid, act very powerfully upon limestone, potash, soda, iron, magnesia, manganese, and various compounds of silica. And then, when the water is impregnated with these, especially with the salts of potash, soda, lime, and magnesia, its dissolving power is again greatly increased, and far surpasses that of water which is merely charged with carbonic acid. It is no wonder, therefore, that hot springs contain a large proportion of mineral matter, and contribute much to the wear and tear of the rocks through which they pass. At Terceira, the hard lava rock from which the hot springs issue first becomes earthy and covered with red speckles from the rusting of the iron which it contains. Then it gradually turns soft, and at length even the glassy crystals of felspar dissolve, and the rock is converted into clay, some of which is quite white from the removal of the iron and looks like the finest prepared chalk, while some is bright red from the accumulation of iron oxide or rust. In England we are far removed from any active volcano, yet we have at Bath hot springs, whose heat, though not so great as those of Aix-la-Chapelle and other places, is still rather startling when we come to consider what it means. The Bath water is not remarkable for the amount of mineral matter which it contains, yet Professor Ramsay has calculated that if solidified, it would in 1 year form a pillar 140 feet high and 9 feet in diameter. All this is now carried away unseen to the Avon, and by the Avon to the sea. The most wonderful hot springs yet known are those called the Mammoth Springs of the National Park of Yellowstone, a tract of country in the heart of the Rocky Mountains. At the northern end of this park, which has an area of 3,575 square miles, rises a greyish-white cliff about 3 miles in length, which on a nearer approach resolves itself into a series of terraces, the steps of which are occupied by numerous natural basins, some gigantic, some minute, and all overhung by clouds of silver vapour. Some of the terraces are several feet wide, others quite narrow, and the steps also vary in height from 10 feet to an inch or two. The top level is 150 feet wide, and here rises the largest spring in a basin 40 feet long and 25 wide. The principal springs occur on the first 10 terraces, and the clear blue water flows down from various openings in the rims of the basins, whose general shape is oval, the edges being scalloped in graceful curves with wavy, frill-like borders, frequently adorned with pearly knobs from the size of a pin's head to that of a hazelnut, or with wonderful incrustations resembling coral, moss, feathers, butterflies' wings, etc. The prevailing colour is a rich cream, but there are touches of bright sulphur yellow, delicate pink and salmon, vivid scarlet, green, rose, crimson, purple, and brown. This beauty is produced by very simple means, and the marble basins, ornaments and all, are merely carbonate of lime coloured by iron and sulphur, and have been deposited by the water. Footnote: there are similar terraces of basins also formed by hot springs at Te Tarata, New Zealand, but these, though as white as marble, are deposited by water containing silica instead of carbonate of lime. End of footnote. The water of the Mammoth Springs, which of course still contains a large quantity of mineral matter, notwithstanding these deposits, flows by several channels into Gardiner's River, and so to the ocean. End of chapter 6.